Picture something the size of the United States, sitting 3 billion miles from the sun, so cold that its air itself falls to the ground as frost. It shouldn't have weather, it shouldn't have seasons, it shouldn't have a climate system at all, not out there, not at 40 times farther from the sun than Earth is, where sunlight arrives 1,000 times weaker than it does on your skin right now, and yet it does. Something up there is behaving like it has a memory, like it has rhythms, like it's alive with a kind of slow, deliberate weather that shouldn't be possible on a frozen rock smaller than our own moon. For decades, scientists thought they understood this place completely. They were wrong. This is Pluto. And what the James Webb Space Telescope just confirmed about it doesn't just rewrite the story of a distant dwarf planet. Stop and sit with that for a second. It rewrites part of the story of how Earth itself might have gotten its atmosphere, its climate, maybe even the conditions that let life happen here at all. Before we go further, if you're new here, this channel is where we take real discoveries from real telescopes and real scientists, and we slow down long enough to actually understand what they mean. No hype for the sake of hype. Just the universe explained. If that sounds like your kind of thing, hit subscribe, because what's coming in this video is one of the strangest atmospheric stories in the solar system, and it's still unfolding right now. Let's go back to the beginning, because Pluto has spent its whole existence being underestimated. It was discovered in 1930 by a 24-year-old named Clyde Tombaugh, working at Lowell Observatory in Arizona, comparing photographic plates by hand, night after night, hunting for a predicted Planet X that astronomers believed was tugging on the orbits of Uranus and Neptune. Tombaugh found something. The world celebrated, the ninth planet, way out past Neptune, guarding the edge of the solar system. But almost immediately, Pluto started disappointing expectations. It was supposed to be massive, big enough to explain those orbital wobbles. Instead, as decades passed and instruments improved, Pluto kept shrinking in astronomers' estimates, first the size of Earth, then Mars, then finally settling at just 2/3 the width of our moon. Not a giant, barely a world at all, by planet standards. In 2006, the International Astronomical Union reclassified it as a dwarf planet, and Pluto became something of a punchline, the planet that got demoted. Then, in July 2015, NASA's New Horizons spacecraft screamed past Pluto after a 9.5-year journey across the solar system, and every low expectation anyone had ever held about this little world got obliterated in a matter of hours. Pluto wasn't a dead, cratered snowball. It had mountains of water ice as tall as the Rockies. It had a heart-shaped glacier of frozen nitrogen the size of Texas, actively flowing like a slow-motion ocean. And highest above the surface, it had something almost nobody expected to see in such detail. Layers of blue haze, dozens of them, stacked in the thin atmosphere like smog rings, visible only because New Horizons caught Pluto backlit by the sun on its way out. That haze was strange. It was beautiful, and at the time nobody fully understood what it was doing up there. New Horizons only had a matter of hours to gather everything it could before it blew past Pluto forever, moving at over 30,000 miles an hour, never to return. Whatever questions that flyby raised, there was no going back to ask follow-ups. Scientists were left staring at a single frozen snapshot of a haze layer they couldn't explain, with no way to watch it change over time. But none of that prepared anyone for what came next. In 2017, a young planetary scientist named Shi Zhang, now at UC Santa Cruz, sat down with the New Horizons data and did something almost audacious. He built a model that treated Pluto's haze not as scenery, but as an engine, a machine quietly running the planet's climate. His idea was simple to describe but strange to believe. Those countless microscopic haze particles, drifting high above Pluto's surface, could be absorbing sunlight during the day and radiating that heat away into space at night far more efficiently than gas alone ever could. If he was right, Pluto's haze wasn't just decoration. It was the thermostat for an entire world. The problem was, in 2017, there was no way to test it. The instruments that existed simply couldn't see faint enough, far enough, to catch a signal that's small at that distance. Zhang's idea sat there, a prediction without proof, for years. That's the first turning point in this story, because everything after this moment is really about whether Zhang was right. The chance to find out arrived in 2022, when the James Webb Space Telescope came online with infrared instruments powerful enough, finally, to separate the faint light of Pluto from the light of its large moon, Charon. Two bodies that from Earth basically blur together into one dim point. Researchers led by Tanguy Bertrand at the Paris Observatory pointed Webb's MIRI instrument, its mid-infrared camera, directly at the Pluto-Charon system and started watching how heat radiated off each of them as they rotated. And there it was, faint but unmistakable. Pluto's haze was glowing in exactly the wavelength Zhang's models had predicted 5 years earlier, direct evidence that the haze wasn't just floating there looking pretty. It was actively radiating heat into space, shaping the temperature of an entire dwarf planet from a layer of atmosphere so thin it's barely there at all. Here's why that actually matters to you. On Earth, our climate is driven mostly by gases, carbon dioxide, water vapor, methane, trapping and releasing heat in ways scientists have modeled for a century. Pluto just showed researchers a completely different way a climate can run, not through gas, but through haze, tiny solid particles acting like billions of microscopic radiators. That's not a footnote. That's a second method nature apparently uses to build weather, one we barely knew existed until an object 3 billion miles away demonstrated it for us. As Bertrand put it plainly, describing this to Live Science, this is unique in the solar system. Which means Earth's own hazy, murky, ancient atmosphere, the one that existed before oxygen, before life as we know it, may have worked on principles we're only now able to understand, because Pluto happened to preserve the demonstration in deep freeze. And Xi Zhang, the man who predicted it in the first place, didn't try to hide how rare this moment was. In planetary science, he said, it's not common to have a hypothesis confirmed so quickly within just a few years. Scientists wait entire careers for that kind of validation. He got it in less than a decade. That's turning point 1. But Webb wasn't finished with Pluto, not even close. Turning point 2 happened almost by accident, on the doorstep next door, Pluto's largest moon, Charon. As Webb's MIRI instrument tracked heat across the Pluto-Charon system, it also mapped out Charon's surface in far more detail than ever before, and something didn't add up. Charon's poles weren't uniform ice like the rest of its surface. They were reddish, a color long visible even in older images, but never fully explained. Webb's new data confirmed what scientists had suspected, that reddish tint comes from methane gas that actually escapes Pluto's thin atmosphere, drifts across the 12,000-mile gap between the two worlds, and freezes onto Charon's poles, where sunlight slowly cooks it into darker, reddish organic compounds over time. Think about what that means for a second. Pluto and Charon aren't just neighbors sharing an orbit, they're locked in an active exchange. One world's atmosphere is quite literally painting the other world's surface. Nowhere else in the solar system have scientists watched this kind of direct atmospheric handoff between two bound bodies play out in this much detail. It's a reminder that even in a place as still and frozen as the outer solar system, matter and chemistry keep moving, keep interacting, keep building complexity. Nothing out there is as static as it looks from 3 billion miles away, including maybe the questions we assume are already answered about how planets and moons shape each other over billions of years. If this kind of thing is blowing your mind a little, that's the point where I'd ask you to drop a comment and tell me which twist in this video surprised you most, the haze acting as a thermostat, or Pluto literally repainting its own moon. I read every one, and it genuinely shapes what we dig into next. Now turning point 3, and this is the one that's still actively unresolved, still being argued about by scientists as you're watching this. While mapping Pluto's surface chemistry with Webb's other instrument, the near-infrared spectrograph, researchers noticed something that shouldn't have been there. A very specific narrow band of missing light, a wavelength being absorbed by something on Pluto's surface that didn't match any molecule in the scientific catalog. Not water ice, not nitrogen ice, not methane, not carbon monoxide, nothing anyone had ever cataloged before, anywhere. At first, researchers assumed it might be a glitch, an artifact of the instrument itself, so they checked it against a completely separate instrument, Webb's mid-infrared camera. The exact same signal showed up there too. That ruled out hardware error. Whatever this was, it was real, and it was sitting on Pluto's frozen surface. Then something even stranger happened. A scientist named Bruno Bézard at the Paris Observatory, who had already found this exact same unexplained signal while studying Saturn's giant moon Titan, a world nearly 1 billion miles closer to the Sun, and utterly different from Pluto in almost every way, decided to ask a colleague a simple question: does Pluto show this same signature too? His colleague Emmanuel Lelouch checked Webb's Pluto data. It was there, the identical unexplained absorption feature, on two worlds separated by roughly 900 million miles, with wildly different sizes, temperatures, and atmospheres. In Bézard's own words to space, it's rather mysterious. We cannot say what it is. Let that sink in. This isn't some vague, hand-wavy claim about aliens or ancient technology. This is two of the most rigorously tested, most powerful scientific instruments ever built, both independently detecting a chemical signature on two different worlds that matches nothing in the known catalog of molecules in the entire solar system. The leading theory isn't dramatic. It's not a biosignature, researchers are careful to say. It's likely a family of organic compounds called alanes, or possibly a familiar molecule whose signature has shifted because it's mixed with other ices in ways nobody has fully mapped in a lab. But likely is doing a lot of work in that sentence. Nobody has confirmed it. As of right now, there is a compound sitting on the surface of Pluto that human science cannot name. Here's why that should matter to you, even sitting comfortably on Earth. Identifying unknown compounds on distant worlds isn't just trivia. It's how we build the chemical playbook for figuring out which ingredients are common across the universe, the same organic building blocks that, on our world, eventually assembled into something that could ask questions about itself. Every unidentified molecule out there is a small crack in our assumption that we already understand the ingredients of a solar system. And right now, Pluto is holding one of those cracks open. None of this, the haze, the color transfer, the mystery molecule, happened because a machine pointed itself at Pluto and spat out easy answers. It happened because people spent years chasing a hunch nobody could prove yet. Zhang published a prediction in 2017 with no way to confirm it, and had to simply wait, not knowing if the tool that could test his idea would even survive its own journey. James Webb launched on Christmas Day, 2021, and had to unfold itself in the vacuum of space, over 300 separate mechanisms, any one of which could have failed and doomed the entire mission before it ever opened its eyes. It traveled nearly 1 million miles from Earth to reach its parking orbit, farther than any repair mission could realistically reach. There was no backup plan. Engineers spent that flight in near silence, waiting through deployment after deployment, hoping a decades-long $10 billion telescope wouldn't be undone by a single stuck hinge. It wasn't. And when it finally turned its mirrors toward a dim 3 billion-mile-old dot that most people had written off as a demoted planet, it delivered exactly the kind of answer scientists like Bertrand and Zhang had been waiting years for. That's the quiet, unglamorous truth behind almost every breakthrough headline you'll ever see. Behind it is a person who made a guess years earlier and simply had to sit with the uncertainty, hoping the universe and the machine built to look at it would eventually agree with them. And this story isn't finished. It's happening right now, in 2026, as you're watching this video. Bertrand and his team's haze findings were published in Nature Astronomy in June 2025, and researchers are still working through follow-up data, trying to understand exactly how the haze's behavior changes with Pluto's seasons. A year on Pluto lasts 248 Earth years, so scientists are essentially watching the opening chapter of a climate cycle that won't complete within any of their lifetimes. Meanwhile, Buzzard's team is actively analyzing newer Webb observations of Titan taken just this year, trying to map exactly where their mystery molecule sits on the surface, whether it clusters around Titan's massive dune fields or spreads more evenly, because that pattern could finally tell them whether it's raining down from the atmosphere or forming some other way entirely. As of mid-2026, they still don't have that answer. The paper documenting the mystery molecule has been accepted for publication in the journal Astronomy and Astrophysics, and scientists across 2 space agencies are actively racing to be the ones who finally name it. And there's a date already locked in that could settle part of this mystery for good. In July 2028, NASA's Dragonfly mission, a car-sized, nuclear-powered rotorcraft, is scheduled to launch from Kennedy Space Center atop a Falcon Heavy rocket, beginning a 6-year journey to Titan. It's scheduled to touch down in Titan's Shangri-La dune fields in 2034, becoming the first vehicle in human history to fly, not just land, on the surface of another world beyond Earth. Once there, its onboard mass spectrometer will be able to directly taste the molecules sitting on Titan's surface, potentially identifying, once and for all, whatever this unexplained compound actually is, not from 900 million miles away through a telescope lens, but by touching it. Zoom out for a second, because this is bigger than one dwarf planet and one strange chemical signal. Pluto sat at the edge of our solar system for over 4.5 billion years, quietly running a climate system nobody thought was possible, hiding a molecule nobody has a name for, slowly repainting the surface of its own moon with stolen atmosphere, and it did all of this in complete silence, unnoticed, until a species on a small blue planet 91 astronomical units closer to the sun finally built a mirror large enough and cold enough to catch the whisper of infrared light it had been sending out the whole time. That's what this really is. Not a story about a demoted planet finally getting revenge. It's a reminder that the universe has been running countless experiments in plain sight this entire time. Climate systems, chemistry, slow atmospheric exchanges between worlds, and we are only just now building the tools sensitive enough to notice. Every one of those unexplained signals is a message that's been sitting there for billions of years, patiently waiting for something to be capable of reading it. And here's the part nobody can answer yet. Not Bertrand, not Zhang, not Buzzard, not anyone. What is that molecule on Pluto and Titan? Nobody knows. It doesn't match a single substance ever catalogued in the history of planetary science. It could be a known molecule wearing an unfamiliar disguise. It could be an entirely new class of compound, born from chemistry that only happens in the specific cold, methane-soaked conditions of these 2 worlds. Or it could be something that reshapes how we think about the raw ingredients available for complex chemistry across the outer solar system. As of right now, in 2026, that question is completely open, and it might stay that way until a nuclear-powered drone the size of a car finally lands on Titan's dunes in 2034 and takes a direct sample. Think about the sheer patience that requires. Buzzard first noticed this signal in Titan data from November 2022. It's now 2026, and he still doesn't have an answer. By the time Dragonfly lands and possibly settles the question, over a decade will have passed since that first strange gap in the light was spotted. That's not a quick headline turnaround. That's most of a scientific career spent waiting on one unanswered question, the same way Zhang spent 5 years waiting to find out if his haze prediction was right at all. Until then, it's just sitting out there, frozen, waiting, unnamed. If this video pulled you in, subscribe and tap the notification bell, because we're going to be tracking Dragonfly and this mystery molecule all the way to that landing. Drop a comment below with your best guess at what that unidentified compound actually is. I want to see your theories. And if you know someone who thinks Pluto is just a boring, demoted rock, send them this video, because clearly nobody told Pluto it was supposed to be boring. Next time, we're heading even farther out, to a world with oceans hidden under miles of ice, where scientists think the actual conditions for life might already exist. You won't want to miss that one.